Jai Hind to all. Today we are here for the third lecture of fluid mechanics, and in the second lecture we have studied about the viscosity and various types of viscosity, its units, capillarity behavior, surface tension and its measurement, and general examples were discussed based on these topics. So let us discuss for the today's slide. This is the table of contents. Today I will discuss with you methods of describing fluid motion, types of fluid flow, and rate of flow or discharge. Next, continuity equation. Continuity equation in 3 dimensions, and last slide will be references. Okay. So, what are the methods for describing a fluid motion? Okay. Basically, based on the review of literatures, there are two general methods which are used for the describing the fluid motion. First one is the Lagrange's method, and second one is the Eulerian method. Okay. In the Lagrange's method, a single fluid particle is followed during its motion, and its velocity, acceleration, density, etc. are described. So, in Lagrange's method of fluid motion study behavior, we considered a particular fluid particle through whole of the fluid motion, and based on this particle behavior, we calculate its velocity, acceleration and density, and these three parameters are enable us to describe the whole behavior of the fluid motion. Is it clear? Okay. Now in the second case, that is the Eulerian method. In this method of the fluid flow, the velocity, acceleration and pressure, density, etc. are described at a point in a fluid flow field, and based on these parameters, the whole fluid behavior is described or interpreted. Okay. So, what are the difference between the Lagrange's method of fluid flow motion and Eulerian method? In case of Lagrange's method, only one fluid particle is considered throughout the whole fluid motion, and based on its property, that is the velocity, acceleration, density, etc., the whole fluid behavior is easily interpreted. Whereas in case of Eulerian method, the parameters, that is the velocity, acceleration and pressure, density, etc., are described at a single point in the flow field. Okay. So, suppose this is a channel in which a fluid flow is continued. Okay. So, in case of Eulerian method, we considered at a certain point. Okay, suppose this is a point. So at this point, let us consider this point as O. Okay, so at point O, all the fluid particles passes through it, and then we consider the parameters, that is the velocity, acceleration, pressure, density. All the parameters are measured here, and using these parameters we describe the whole fluid flow motion. Okay. Now the Eulerian method is commonly used in fluid mechanics. So now we are going to use the Eulerian method of fluid motion method. Okay. Let us move towards the next slide. what are the various types of fluid flow? Various types of fluid flow. Now, the fluid flow is generally classified as, first one is the steady and unsteady flows. Second one is the uniform and non-uniform flows. Third one is the laminar and turbulent flows. Fourth one is the compressible and incompressible flows. Fifth is the rotational and irrotational flows. And the last one, that is the sixth is 1, 2 and 3 dimensional fluid flows. So these are the general fluid flow classification, which are basically described here one by one. That is the steady and unsteady. So steady means its meaning is basically constant. Steady means constant, whereas unsteady means variable. So in steady and unsteady flow, let us discuss in details. In steady fluid flow, the fluid characteristics like velocity, pressure, density, etc. at a point do not change with the time. So what is the steady fluid flow? In case of steady fluid flow, the fluid characteristics, that is the velocity, pressure and density, these parameters are called the fluid characteristics, does not change at a point with respect to time. So if you want to represent it mathematically, then we can write it as del V by del T at x0, y0, z0 is equal to 0. Okay. In similar way, del P by del T at point x, y, z equal to 0. And del density divided by del T at same point will be 0. Okay. So in case of steady fluid flow, all the fluid characteristics, that is the velocity, pressure and density at a point do not change with respect to time. And in case of unsteady fluid flow, these three parameters changes with respect to time. In case of mathematical way, we can represent it as del V by del T at point x, y, x0, y0 and z0 is not equal to 0 because it is continuously varying. Okay. Next, uniform and non-uniform fluid flow. In case of uniform fluid flow, the velocity at any given time does not change with respect to space, that is length of direction of the flow. We can also represent it in a mathematical way, that is the del V divided by del S at time t equal to constant is equal to 0. Okay. So in case of uniform fluid flow, velocity at any given time does not change with respect to space in the direction of fluid flow. Okay. In mathematical way, we can represent as del V by del S at time t equal to constant equal to 0, where del V is the change of velocity, del S is the length of fluid flow in the direction S. Similarly, in case of non-uniform fluid flow, it is that type of fluid flow in which the velocity at any given time changes with respect to space. So if any parameter changes with respect to space at any given time, then it will not equal to 0. Okay. So in mathematically, we can represent it as del V by del S at time t equal to constant will not be equal to 0. Okay. So in case of uniform and non-uniform, we only consider one parameter, that is fluid characteristic is the velocity of fluid flow. So in case of uniform fluid flow, the velocity variation with respect to time in a particular direction will equal to 0, whereas in case of non-uniform fluid flow, the velocity at any given time changes with respect to the space. Okay. Now next definition is the laminar and turbulent fluid flows. So in case of laminar fluid flow, it is defined as that type of fluid flow in which the fluid particles move along well-defined paths or streamline, and all the streamlines are straight and parallel. So there are certain important words which you have to keep in mind. In case of laminar flow, it is defined as that type of fluid flow in which the fluid particles move along well-defined paths. Suppose so here you can see it that it represents the well-defined path in which fluid particles are moving. Okay, so this type of fluid flow is known as the laminar fluid flow, in which the fluid particles move along a well-defined path and all the streamlines are straight and parallel to each other. Okay, so these lines are known as the streamlines. Okay, streamlines, and these lines are always parallel during the laminar fluid flow. Now, in case of turbulent fluid flows, it is that type of fluid flow in which the fluid particles move in a zigzag way. Zigzag way can be represented in this way. Okay, this is the zigzag way. You can also represent it as. Okay, so this type of fluid flow pattern is known as the zigzag way. So due to the movement of fluid particles in a zigzag way, the eddies formation takes place, which are responsible for high energy loss. Okay, so in case of turbulent fluid flow, all the fluid particles move in a zigzag way. Okay, suppose direction of fluid flow in this direction. Okay, so in this type of fluid flow, all the fluid particles move in a zigzag way. Due to this type of movement, eddy formation takes place. Eddy means at certain point it will behave like this type of fluid flow. So during the eddy formation, high energy losses will occur. Okay. Now there is another important point in case of laminar flow. Thus, the particles move in a laminar or layers, gliding smoothly over the adjacent layer. So in case of laminar fluid flow, the particles move in a laminars. Laminars means layers. Okay, gliding smoothly over the adjacent layer. This type of flow is also called as a streamline flow or viscous flow. So in question paper, if it is mentioned only viscous flow, it means it is a laminar flow. Okay, or it is also known as a streamline flow. Sorry. In case of laminar fluid flow, all the particles flow in a well-defined pattern, whereas in case of turbulent fluid flow, the fluid particles move in a zigzag way. Okay. Now, for a pipe flow, the type of flow is determined by a non-dimensional number called the Reynolds number. Okay, and it is represented as Vd divided by nu, where V is the mean velocity of flow in a pipe, capital D is the diameter of pipe, and nu is the kinematic viscosity of fluid flow. This term is already discussed in the first lecture. Okay, so there is a basic criteria which enable one or us to determine whether the fluid flow is laminar flow or turbulent flow. So how can you determine the type of fluid flow? One can determine the fluid flow by calculating the parameter, that is the Reynolds number. Calculating the Reynolds number, and Reynolds number can be represented as capital R, and it can be written as R equal to Vd divided by nu. So these parameters uses for calculation of the Reynolds number, and based on the Reynolds number value we can easily determine whether the flow is laminar or turbulent. Okay. Now, if the Reynolds number is less than 2000, the flow is called laminar. If the Reynolds number is more than 4000, it is called turbulent flow. And if the Reynolds number lies between 2000 and 4000, sorry, if the Reynolds number lies between 2000 and 4000, then the flow may be laminar or turbulent, or you can easily say it as transition flow. Transition flow means it may be laminar or turbulent. Okay, so using the Reynolds number value, you can easily classify whether the fluid flow is laminar or turbulent. If the value of Reynolds number is less than 2000, then it is known as the laminar flow, in which all the fluid particles move in a straight line, in a well defined pattern. Okay, and if the value of Reynolds number is more than 4000, it is known as the turbulent flow, where all the fluid particles move in a zigzag way. Okay, in this case eddy formation will take place and high energy losses will occur. Okay, and if the Reynolds number value is lie between 2000 to 4000, this stage may be laminar or turbulent, or simply you can say it as a transition stage. Okay. So next, 1, 2 and 3 dimensional fluid flow. So in case of one dimensional fluid flow, the flow parameter such as velocity is a function of time and one space coordinate only, say x. So in one dimensional fluid flow, the fluid parameter such as velocity is a function of time and one space coordinate only, say. For example, if you want to represent not V, if you consider, suppose u is the velocity in particular direction. So here u is represented as the velocity in x direction. So it is basically a function of time and space. So time t and space in only one coordinate. Okay. So in this case, that is the one dimensional fluid flow. The fluid parameter, if we consider the fluid parameter as velocity, so velocity will be a function of time and one space coordinate, suppose it will be x. So here you can represent it as u is a function of t and x. Okay. Now for studying one dimensional flow, the velocity is a function of one space coordinate only. The variation of velocity in other two mutually perpendicular directions is assumed negligible. So in case of study one-dimensional fluid flow, velocity is a function of one space coordinate, that is, let us consider x in x direction, okay, and the variation of velocity in other two mutual perpendicular directions is assumed negligible. Okay, that is, suppose this is a x direction, suppose this is a y direction, and this is the z direction. So in case of study one-dimensional fluid flow, velocity is only a function of one space coordinate. Suppose it is x. So in case of study one-dimensional flow, the velocity variation in other mutual perpendicular direction is assumed to be negligible. Okay. Hence, mathematically, for one dimension, u is a function of x, where v equal to 0 and w equal to 0. So what is the meaning of u, v and w? U is the velocity of fluid flow in x direction, v is the velocity of fluid flow in y direction, and w is the velocity of fluid flow in z direction. So u, v and w. Okay. So u is the velocity in x direction. Similarly, y and u, v and w are the velocity in corresponding y and z direction. Okay. So mathematically you can represent it as a u is a function of x, that is the one space coordinate. Okay, and it is also a function of time. Okay. Now two-dimensional fluid flow, it is that type of fluid flow in which the velocity is a function of time and two rectangular space coordinates, say x and y. Okay. For study two-dimensional fluid flow, the velocity is a function of two space coordinates only. The variation of velocity in the third direction is negligible. So mathematically you can write it as u is a function of x and y, or v is a function of x and y, okay, and w is equal to 0. Now third, a three-dimensional fluid flow. It is that type of flow in which the velocity is a function of time and three mutually perpendicular directions. Similarly, in study three-dimensional fluid flow, you can write it as u is a function of three space coordinates x, y and z. Similarly, v is a function of x, y and z, and w is a function of x, y, z. Now next topic is the rate of flow discharge. It is represented as capital Q. Now it is defined as the quantity of fluid flowing per second through a section of a pipe or a channel. So how can you define the rate of discharge, capital Q? It is defined as the quantity of fluid flowing per second through a particular section of pipe or channel. In case of incompressible fluid, incompressible means real fluid, the rate of flow or discharge is expressed as the volume of fluid flowing across the section per second. So in case of incompressible fluid, we can define the rate of discharge, capital Q, as volume of fluid flowing across the section per second. Means Q equal to volume of fluid flow per second, means time. Okay, through a particular section, at a section. Okay, section to be fixed. Now in case of compressible fluid flow, the rate of flow is usually expressed as the rate of fluid flowing across the section. Okay, in case of compressible fluid, means real fluid, it is measured as the rate of fluid flowing across the section. And if you talk about the unit of discharge, rate of discharge, then for liquids the unit of Q are measured in meter per second or liters per second, In case of gases, the units of Q is kilogram force per second or Newton per second. Now, next slide is, consider a liquid flowing through a pipe in which A is the cross-sectional area of pipe, V is the average velocity of fluid across the section. Then the discharge Q can be written as average velocity into cross-sectional area. So Q is measured by using this equation, that is the 5.1. Q equal to cross-sectional area into average velocity through the section. Now, next is the continuity equation. The equation based on the principle of conservation of mass is called the continuity equation. So, what is the continuity equation? The equation which is based on the principle of conservation of mass is known as the continuity equation. Now, for all liquid or fluid flowing through the pipe at all cross section, the quantity of fluid per second is constant. If we consider a section or pipe at different sections, suppose this is the section 1 and this is the section 2. So suppose fluid is flowing through this pipe. So at any section, the quantity of fluid flow per second is constant. Okay. So considering these two cross sections, that is the 1 and 2, let us assume some symbols, that is the V1 is the average velocity at cross section 1. There V1 is the average velocity, ρ1 is the fluid density at section 1 and A1 is the cross sectional area at 1. Similarly, V2, ρ2, A2 are the corresponding values at section 2. Means this value will be ρ2, A2 and V2. Density, average velocity, cross sectional area. Okay. So if you use the formula, that is the quantity of fluid flow per second remain constant at these two cross sections, then what is the rate of flow at section 1? This will be equal to the ρ1 A1 V1, and according in the similar way at section 2 will be ρ2 A2 V2. Now, law of conservation of mass, rate of flow at section 1 will be equal to the rate of flow at section 2. So it can be written as ρ1 V1 A1 equal to ρ2 V2 A2. And this is the general equation for the continuity equation, which you can use for the further numerical problem. Okay. If the density of fluid is constant and same, then its value will be equal to these two sections. So ρ1 will be equal to ρ2. In that case, ρ1 and ρ2 will be cancelled out. So final equation will be A1 V1 equal to A2 V2. Okay. Now let us discuss problem. The diameters of a pipe at sections 1 and 2 are 10 cm and 15 cm respectively. Means here the diameter is given. D1 is 10 cm, D2 is the 15 cm. Find the discharge through the pipe of the velocity of water flowing through the pipe at section 1. Find the discharge through the pipe. Means you have to calculate the value of discharge, that is the capital Q, through the pipe. If the velocity of water flowing through the pipe at section 1 is given as 5 meter per second, V1 is given here. Determine also the velocity at section 2. Means we have to calculate here V2. Okay. Now put all the given value, that is the D1 is 10 cm. You can convert in SI system 0.1 meter. Cross sectional area of this pipe can be calculated using pi by 4 D1 square. So put the value of D1 0.1 meter. So final value of A1 will be 0.007854 meter square. And V1 value is already given here. Similarly, at section 2, D2 is given and A2 can be calculated using D2. So this will be equal to the 0.01767 meter square. Now use the formula of the Q, that is the Q at section 11 will be given as A1 V1. So A1 is already given and V1 is already given. Using this formula we can calculate the rate of discharge through section 1. So this will be equal to the 0.3927 meter cube per second. Okay, and from the continuity equation we know that the rate of discharge through these sections will be equal. So using the continuity equation, A1 equal to A1 V1 equal to A2 V2. So here V2 can be calculated A1 V1 by A2. So A1 V1 is already calculated here. A1 V1, okay, and A2 is already given in the problem. So putting all these values, you can calculate the value of V2. It will be equal to 2.22 meter per second. Okay. This is the continuity equation in 3 dimension. This is the derivation. I will cover it in short way. So what is the continuity equation in 3 dimension? Consider a fluid element of length dx, dy and dz in direction of x, y and z. And small u, small v and small w are the inlet velocity components in x, y and z direction respectively. So mass of fluid entering the phase A, B, C, D. Suppose this is the fluid element A, B, C, D, E, F, G, H. So the mass of fluid entering through the phase A, B, C, D. A, B, C, D. Okay. It will be equal to the density into velocity in x direction into area of A, B, C, D. Okay. This value equal to the per second. So density is already given, standard value density rho. Velocity and direction is represented as small u, and area of phase A, B, C, D will be this is in y direction, so dy, and this is in z direction, this will be bj. Then mass of fluid leaving in the phase E, F, G, H per second will be rho u dy dz plus del by del x rho u dy dz into dx, and this value will increases by the discharge. Okay, of phase E, F, G, H is E, F, G, H. This increase of value will result due to the fluid flow passing through this length. Okay, so this is the mass of fluid leaving through this phase per second. Now gain of mass in x direction will be mass through A, B, C, D minus mass through E, F, G, H. Okay, so put all this value, that is this value A, B, C, D minus value of mass leaving through E, F, G, H. So if you put this value, then final value will be equal to this final value will be equal to minus of del by del x rho u dx dy dz. Similarly, the net gain of mass in y direction will be minus of del by del y rho v dx dy dz. And in z direction it will be equal to minus of del by del z rho w dx dy dz. If you want to calculate the net masses, net gain of masses, then it will be summation of in all this value. So it will be equal to minus of del by del x rho u plus del by del y rho v plus del by del z rho w into dx dy dz. Okay. Since the mass is neither created nor destroyed in fluid element, then the net increase of mass per time in the fluid element must be equal to the rate of increase of fluid flow in this element. But mass of fluid element is rho into dx dy dz, and its rate of increases with time is del by del t rho into dx dy dz, or you can easily write it del rho by del t into dx divided dz. So equating these two values, you will get minus of del by del x rho u plus del by del y rho v plus del by del z rho w into dx divided dz equal to del rho by del t into dx divided dz, and the common value will cancel out. So final value will equal to del rho by del t plus del by del x rho u plus del by del y rho v plus del by del z rho w equal to 0. Okay. Now equation 5.3 is continuity equation in the Cartesian coordinate in its most general form. So this equation is applicable for the steady and unsteady fluid flow, uniform and non-uniform fluid flow, and compressible and incompressible fluid flow. For steady fluid flow, we already know that del rho by del t equal to 0. Hence, the equation 5.3 will be equal to del by del x rho u plus del by del y rho v plus del by del z rho w, and let us take the common value outside. So final value is equal to del u by del x plus del v by del y plus del w by del z equal to 0. Okay. If you equation 5.4 is the final equation. If you equation 5.5 is considered as the continuation of 3-dimensional equation, for 2-dimensional fluid flow, it will be reduced as del u by del x plus del v by del z. Okay. So this is the for today lecture. I hope that you have enjoyed, and this is the references. I have taken this material from the textbook of fluid mechanics and hydraulic machine by R.K. Bansal. Thank you to watch my lectures.